Welcome to the module on quantum error correction. In this video, we will talk more basic stuff and we will introduce a few examples of real quantum error correction codes. In the previous video, we looked at the bit flip code and we talked about the trick to use redundancy to encode logical quantum states into multiple physical qubits. For example, you can encode the logical 0 into the state 0, 0, 0 and the logical 1 into the state 1, 1, 1. And this code we call the bit flip code. We construct circuits such as the one shown here, where we can use parity measurements to detect whether an error occurred. In this case, whether a bit flip error occurred. And we can then subsequently correct the error by applying appropriate correction gates to the qubits. Now, what we actually did here is that we measured these two operators, Z1, Z2, or the operator Z2, Z3, or let me write it sort of in the full 3 qubit space as Z1, Z2 times the identity on the qubit 3, or identity on qubit 1 and Z2, Z3. These operators in the language of error correction codes we call stabilizers, and the logical states are actually the +1 eigenstates of the stabilizer operators. And in general, we can actually introduce any error correction code in terms of their stabilizers, and that makes it a very useful way of talking about the error correction code. Similarly, it's also useful to talk about the logical operators. So in a single qubit, you have a Z operator and an X operator, which are the Pauli operators. In the same fashion, we can define Pauli operators for the logical qubit, and we can do that by constructing them through the physical qubit operators. So in the bit flip code, the logical Z operator is Z1 times Z2 times Z3, and the logical X operator is X1 times X2 times X3. It's important to note that these operators, these logical qubit operators, all commute with the stabilizer as they must, because that means we can encode qubit information into these logical operators, and we can measure the stabilizers without destroying the information encoded in these logical operators. An important fact of these logical operators is that you see they are constructed by 3 operators, so Z1, Z2, Z3. And the number of Pauli operators in the logical operators is something we call the code distance. And it relates to how many errors we can actually correct in during the detection and correction part of the quantum error correction. In this case, the code distance is 3, and that means we can correct 1 error when we try to do error correction. For the phase flip code, we can treat it in the similar fashion in the stabilizer formalism. So we looked at the logical states, which are plus, 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 or minus, 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 which corresponds to eigenstates of the stabilizer operators x1, x2, and the other one x2, x3. The logical operators for these codes look very similar to the bit flip code, except they are swapped. And again, it's a distance-free code, which in this case means we can correct 1 error. Now, we want to be able to do bit flip and phase flip correction at the same time. And a trick to do that is by concatenating the bit flip code with the phase flip code, meaning we construct a phase flip code out of logical qubits that encodes the bit flip code. This construction is called Shor's error correction code. And it can detect 1 bit flip error and 1 phase flip error per cycle. Now we have introduced the stabilizer formalism, and that allows us to quickly write up the stabilizers for the Shor's error correction code as these operators that you see here on the right. They are color-coded in this form because you see there's a number of them that are all Z operators, like in this case pairs of Z operators multiplied together. They are bit flip code-like in their construction, meaning they detect bit flips in the Shor error correction code. And similarly, we have these 2 phase flip-like operators that detect phase errors on Shor's error correction code. You notice that these are all either products of sets or all products of X, and codes that have this construction that we have bit flip-like operators or stabilizer operators, and phase flip-like operators are called CSS codes, and they lend themselves to an easy interpretation of the logical states of the code. In this case, the logical operators here is, for example, either x1, x2, x3, or x3, x4, x5, x6, and so on. And while the X logical operator is actually a product of all 9 set operators. Here, the distance is set by the smallest of these distances. So this means that in this case, the distance of the code is a distance 3. And you notice that we have actually 3 choices of logical set in this case. That's a feature that can help you decode the errors in a more advanced scenario. Not every code is a CSS code. An example is the smallest possible code that we can construct that can detect either phase flip or bit flip errors. It's called the 5-qubit perfect code, and you construct them from the stabilizers that you see here on the right. As I said, this is not a CSS code, but it's a nice code to look at because it really is the smallest error correction code that we can construct. So in summary, we have now defined stabilizers that we can use to construct error correction codes. We have looked at 2 examples of how the stabilizers look for real error correction codes that can detect both phase flip errors and bit flip errors, the Shor error correction code, and the perfect 5-qubit code. And we talked briefly that distance tells you how good the code is. And in the next module, we will look at some examples of larger codes.